measure the angles of a geodesic triangular, say on a curved surface, and you know always like the interior sum of these these angles. So you have geodesic triangle is if you have K being strictly positive, we have that the sum of all these interior angles of the triangular, so P1, P2, P3. So, for example, we are on the sphere. Then what we get from this theorem is that this sum over here is strictly positive, strictly larger than pi. And for example, on the sphere, you can realize that if you have for example, we could take the triangle so we go to the North Pole, and then we go down to the equator, and we hit the equator in a 90 degrees angle, and we go down in a different direction. So then we already have two angles which are 19 degrees. So that's already larger than pi. Then we have some angle over here. Conversely, something that you actually know from kindergarten, hopefully, is that if you're on a plane and you take a triangle and then you take the angles in the triangle, you always get pi. And if the Gaussian curvature is always negative, then these angles sum up to something that is less than pi. Okay. So I think that's like a good point to go on a break, because by now we understand very much like this part over here. The whole integral over of the Gaussian curvature of a small part of the surface, we can calculate now. We can like say that's like, okay, that has something with a geodesic curvature, and then we just need to, at least like get some angles that are coming from the triangle, but essentially we know that we get some number of pi there. So that's like the small triangle. So like the next, after the break, what we will discuss is like how do you build like a whole surface out of small triangles? Because then what we can do is we just like take the sum over all of these triangles of this expression, and then we get something. And that something hopefully will correspond to the Gauss-Bonnet theorem, where we can number the holes. So that's the whole idea for the second part. But then let's continue in 15 minutes, so 10 after 7. Okay, let's continue. Before we come to some organizational remarks, one final, like maybe summary, what we did so far is the following, that on this side here, we have this integral of the Gaussian curvature over some small area. And for that, you need to know the Gaussian curvature on the whole area that we have. Like if you have like that sphere, then the Gaussian curvature, you need to know the Gaussian curvature on that whole thing to calculate this expression. But the nice part is about the rest of that equation, like all of these, they just involve the geodesic curvature of the boundary and the number of angles of the boundary. So that's an information that is only on the boundary. You don't need to know anything on what is like happening inside of the area. So that's perhaps like the most important step in the whole proof of the Gauss-Bonnet theorem is that allows you to say like information in a relatively large area. You can like encode that whole information of the Gaussian curvature just by looking at the boundary curve and collecting information on the boundary. And then we put them now together to make it like cover like the whole surface. So that's the main part that we did so far. And like the proof of that was essentially Stokes' theorem. So that's, yeah, like you should remember that part. Okay. Now, two more organizational remarks. The first one, I would like to thank everyone who gave feedback. It was very helpful, where you had like good suggestions, and it was really good to see what you liked and what you see to make better. One of them things was that like my handwriting is not so good, and I'm sorry for that. I try to get better. I think I got better, but it's still not like where I want to be. So what I would like to do for the next generation of students would like to have at least some handouts or some notes so that they can go through it, because I also picked some of the books. That was also feedback that I like don't follow like a book very linearly, but like pick out like some stuff from one book and combine it with another book. So I would like to have some lecture notes, in the best case like some LaTeX format that I can like distribute to maybe even like this semester still, but definitely for the next year. So if someone made some digital notes of some form, if you use LaTeX, Obsidian, whatever, if it's digital, please send me an email or WeChat or come afterwards after the lecture to me, and then we can discuss that. It's totally fine if it's not perfect. If there are typos in there, also no problem. It's just like having something is already better than having nothing for the next student. So that would be nice if you can contact me, and maybe I can even give you a nice thank you for that. So that's the first part is the lecture notes. The second one is if you like geometry or you liked some, you liked like mathematical physics in general, please get in touch with me. Last year there were 2 students that like continued working with me as part of a summer project, and both of them are now doing also their bachelor thesis with me. So you have here Han Fang. Like both of them actually went to Utrecht summer school in geometry. So they both liked that a lot. If you want to have any questions of how they enjoy or like what they liked or what they didn't like with working with me, feel free to send them an email. I will also put the WeChat contacts later in the group. So if you have any questions, either contact me or the students directly. It's totally fine. So yeah, like I would love to have some more students like that do some geometry courses and summer projects or bachelor thesis. So please get in contact if you liked lecture in general. Good. So now we are back to more geometry, and the idea is a bit like summarized in this picture is that we would like to cut out now we kind of like want to assemble our big surface that we have in small triangles, because for triangles we understand that quite well, what happens to the total Gaussian curvature. So now we would like to see how it's for the whole surface, and the idea is to assemble your surface in triangles and then pitch them together. So that's the main idea. And you might ask yourself, why triangles and not like some other angles? Like, why you need like polygons of 3? And like the idea is mostly that they have a nice combinatorics. So suppose you're in a sphere. And suppose you have two points, and they are connected by two edges. Two edges, and the idea is now that we count the number of vertices or points, and we count the number of edges that we have, and we count the number of faces, so like two-dimensional areas that we get if we cut our surface. So here we have the sphere. So okay, it's not a very beautiful sphere, but what we have is we have say like these 2 points. They're connected by one edge, and then say I walk around the sphere to get like another edge, and then I count how many of these geometric data I have. So what we have is we have 2 points, and the edges are like also 2. We have this one edge and this other edge. And faces, we have the upper, say like the upper half and the lower half. So we have 2 different faces that are like made our surface. So that would be just the counting. And what happens now if you remove one edge? So what happens there if you remove one edge? So how many points do you still have? You still have 2 points. If you remove, say, the blue edge, or like, say, the red edge is maybe easier. So if you just remove this one edge, then we still have the blue edge left and the 2 red dots. So in this case, we have 2 points, but only one edge. But also, our surface is no longer like split in 2 faces, but you only have one face, because you can go from this upper to the lower part without crossing an edge. So in this case, we have only one face. And now if you move the points together, then they merge to 1. So what happens in this case? So if you move the red points together so that they lay on top of each other, what we get up is we end up with one number of points because they are like on top of each other. We only have one edge, namely the blue one, but which is going around now one circle. But now we end up, that would be one way, but let's say, if you move actually along the blue edge, which we still have, then the blue edge is removed, so we actually don't have any edge. And faces, we also only have one face left because it's the whole sphere. So it's like just like a single point with no edges and one face. And you can play around a little bit more. That was just like to give you some examples of that. Like the geometry really depends like quite a bit on what happens. Like if you remove points and edges or like you add them, then also the number of faces changes. So that's quite apparent that there will be some relationship between them. Then you can't change like just like arbitrary things. And in general, we have the following observation. If you remove an edge, then it also removes a face. And if you merge two points, then it also removes the edge that connects between them. So in total, around that observation is that the number of points minus the number of edges plus the number of faces is not changed. So if you do the calculation, up here we have 2 points, 2 edges, and 2 faces. So if you take the sum up there, or with the minus sign, what you end up with is 2 here. But also you have 2 points. You have 1 edge and 1 face. So these add up, and we get 2. And here you can also convince yourself that you get 2. So that's the main idea why we like triangles, is that like these faces, you have this nice combinatorial effect that points minus edges plus faces give you some constant that doesn't depend too much on like how many edges and stuff you get. And then the idea is, of course, if you make that with triangles, you get what is called a triangulation of your surface. And that's the next definition. A finite number of triangles call them just triangle with a J, which are living, of course, in our surface. So surface S, and which have two properties, which they cover all of S. So if you put all of the triangles together, you get like the whole surface back. And if two triangles intersect, then they do so in a common edge or point. And each triangle is oriented in a way that is compatible with the orientation of the surface. So the second point just means that, for example, you can't have a picture like this where you have one triangle and then another triangle like this, and the third triangle would be this. So you can't have that because all of these, like say the green and the white one, they intersect. They have like these edge in common, but it's not like the whole edge because it's not like the whole edge of this triangle. So what you would need to do if you get like like a proper triangulation would be you need to cut this over here to get like really that the white one and the green one share really one edge and only like the whole intersection is one edge. Or you can have something like at a triangle like this one and this triangle are matching only in this one vertex. But they're really like, they have to have like the whole edge together and not like half of the edge together. So that's what is called a triangulation. So for example, here we have a triangulation of the sphere, and I let you calculate for a second how many points, edges, and faces are there in this particular triangulation. Okay, how many points do we have? That's easy. 4. Okay, how many edges do we have? Yes, 6 edges. And how many faces? Yes, exactly. So in this case, what do we have for the points number edges plus faces would be 2. And this number is called the Euler characteristic. Of a triangulation. It's usually denoted by chi. So chi is the number of points, or usually it's also called the vertices minus the number of edges plus the number of faces. So what we had like as an example based on this calculation, the sphere has Euler characteristic of 2. So what do we do for the torus? The torus is quite involved actually to get the triangulation correctly. So what you can do is you cut it open 2 times on these two circles, these big 2 circles. So that's step number 1. Then we get like some kind of like tube, and then we cut the tube like open. That's like what is done here. So what we get then is like just 2 like the red one is in a rectangular, the blue one is a rectangular, and same for the yellow and the green. And then we cut like each of these rectangulars again half. So what we end up with is then this following triangulation of the torus, which is actually a bit more involved. So one way to represent it is like the torus in this way, where we have like just a square, and the torus is get by gluing this side over to this side, and this side of the like we glue with that. So that's the torus. And if you plot it in the picture, you get something of that sort. And in this case, we have, I think I give you, just because it's a bit easier, we have 9 points in this case. Edges are 27, at least if you calculate the mean and then you, how you get. And then faces, we have 18 faces. So in this case, the torus, we end up with 0. But actually, like one point that I like have not told you yet is like we just calculated that for a certain triangulation of the sphere and for the torus. Like who tells you that we do it for the different triangulation? Maybe we cut like some more triangles that we get the same number. For example, we can like ask what is the minimal triangulation of the torus, like that has the least number of edges here. And here's one, for example, with 7 vertices or points and 14 faces. So there's many different ways to get that, and that's actually the minimal triangulation of the torus that has the least number of vertices. So we need a few results about these triangulations, which I will just state without giving the proof, because it's more like a topology class actually. But they build essentially on these 2 observations that if you remove certain edges, then you also get faces and stuff like that. So we have the following proposition. The first one is that every compact surface maybe even with a boundary, has a triangulation. So that's the first result. It's intuitive, relatively clear. What you do is you just take scissors and cut your surface, and then you get like something that is smaller, and you keep cutting everything until you just get like triangles in the end. So that's the proof by construction of like, but it's not like actually the real proof is pretty involved, because you might end up with very involved objects after cutting. So yeah, like I don't want to give the proof, but there's a result that says like you can have every compact surface, you have a nice triangle ligation. We can arrange that every triangle is covered by some chart, by one chart. So the triangles are relatively small, so that they can be covered by one coordinate chart, and that's important because we can arrange that they always admit a global frame, which is of course important because we want to apply those results that we had earlier, which needed a global frame. So we can apply the results that we had earlier to each of these triangles. There is a statement that says the Euler characteristic is the same for every triangulation. So the chi that we defined, which was a priori something that depends on the triangulation, now is actually the same. So it only depends so all of these different triangulations that I showed you before, they all give you the same result for the surface. So we can write that chi of S instead of chi of the triangle ligation. So that really depends only on the surface. And then we have another result that says that if phi is a map from one surface into another surface, and it's smooth and bijective, so points in both surfaces are in one-to-one correspondence with each other, and we have a triangulation of S then we also get a triangle, then we can push it forward, just move it on the target by mapping it. That's a subset or collection of subsets, and that one is a triangulation of S prime. And importantly, like vertices are mapped to vertices, edges are mapped to edges, and faces are mapped to faces. So in particular, the Euler characteristic of S and the Euler characteristic of S prime are the same. So that in particular means that if you deform your surface slightly, so you just like deform it a little bit like what I had before with the sphere, and you make it like a handlebar, then you just have like a nice bijection, because you see you can track where like each point went, and that means that the chi, it doesn't change under these operations. And in fact, a bit surprising perhaps is like that the opposite is also true, that if you have two compact surfaces that have the same Euler characteristic, then there exists a bijective map between them. So for example, one application of this fact is in computer vision. For example, you can say you have like an object, like say like input A, and you can put like some graphic designer said like, okay, I put like a nice giraffe texture on that, and then you say like maybe we have a small one or like some small other animal, and you can look at the, like, okay, like if they have the same Euler characteristic, or what you do is like you do triangulations of them, which in a computer vision is actually a very natural thing to do. So you build up your objects out of triangles, and then if you calculate the Euler characteristics of both of them, you know there exists a bijective map between these two surfaces. And if you have a nice bijective map, what you can do is you can map the texture from this one object onto here to get like the texture transferred from this giraffe to a whatever other animal that is over there. So that's one way to use that, for example, in computer vision. And usually, like the first example over there is like in computer vision, what happens usually is, if, for example, if you want to triangulate a face, is that you need like adaptive mesh. You usually put a lot of triangles where you have a lot of curvature. So that's like displayed here, is that usually if you do it like very coarse-grained, then you kind of lose the geometric features. But if you are a bit more adaptive and like put smaller meshes over where you have a lot of curvature, then you usually get like quite a good result of your original picture. So that's also one application of curvature back to areas like computer vision. So that's one example of like where we can use triangles and triangulation outside of mathematics. Okay, so the last step that I have to tell you is what is the relationship through the Euler characteristics and the number of holes. So that's like something that is not clear, right? Like because we had like what is this number, the points, edges, and faces with this strange minus sign. What does this have to do with the number of holes that you have in an object? And the claim here is the following, that the Euler characteristic is minus 2 times the number of holes minus 1. So the proof is kind of by induction. So what we have seen already is that for the sphere, the Euler characteristic was 2, which would be okay because the number of holes of the sphere is 0. So in this case, we just get 2. So that's in the number of holes would be 0. For the torus, we have seen that chi was 0, which is also correct because the number of holes would be 1, so the right-hand side gives you 0. So it's already there. So the general case follows them from this construction that if you have your surface and it might have like already some kind of numbers of folds that you already understand, and you would like to add one more, what you can do is we just take a torus and we would like to glue them together. So what you do is you